I did an older video where I found some toroids at the junk store and I built this filter. It's a low-pass filter for a 7 megahertz transmitter, so it's a 40 meter low-pass filter for transmit, and it allows 7 megahertz to go through, and then it rolls off. And I think I measured this, and we did a bunch of stuff. But I have a new tool, so yeah, I want to take a look at this particular filter on my new network analyzer. So let's go do that. All right, so the filter, I want to be making a transmission measurement. Okay, so that's also known as S21. People aren't familiar with analyzers. This is the channel 1 port, this is the channel 2 port. This one's called reflection, this one's called transmission. So reflection outputs radio waves and then inputs radio waves and looks for the reflection. And the transmission port only looks at incoming RF, right? So this is basically, even though this one says transmission, it's transmitting out this one and into that one, so it's a bit confusing. So this one forces out and measures in, and this one only measures in. And so the signal is going to come out of this connector, going through the filter, and then it's going to go in this side, and we're going to measure the frequency response from input to output. All right. So you can set your network analyzer up to do various things. So the first thing I'm going to do is I want it to be very, very fast. Okay. So if you're in an R&D situation and you're building a prototype, you're not caring about absolute numbers quite yet. You just want to be able to tweak things in very, very quickly. So that's one of the benefits of having a nice spectrum, a network analyzer like this, is it can be very, very fast. So if we want to speed it up, one of the things we can do is choose the number of points across the screen. The fewer number of points, in fact, it'll do 3 points across the screen. Wow. Or you can go all the way up to 1600 points across the screen, and then you can see that it's scanning much, much slower. So we want to have something. We want to have something pretty fast. Let's go ahead and do something crazy like 51 points. Okay, and you're saying, well, that's going to be really terrible, but we'll see. We'll do 51 points. All right. So we want to set this thing up. We want to have some frequency range. Now, this is a 7 megahertz filter. All right. So we're going to set up some frequency range. We're going to start. At say 1 megahertz, and we are going to go up to 40 megahertz. Okay. Let's see, 40 megahertz. All right. So we're now measuring between 1 megahertz and 40 megahertz, and you're saying, well, this is still pretty slow. We can do sweep time though. We can lower the sweep time. So now we're sweeping at 31 milliseconds, right? So that's very, very fast. All right, and let's just throw on, we don't need to calibrate, we don't need to do anything, we're just gonna throw it on just to kind of see what we're gonna see, okay? And so, a lot of times you don't need to calibrate these things if you're just trying to get some type of relative measurement. And there we go, it's a filter. And we are starting off transmitting, and then it's rolling off, and it's not transmitting over here, right? It's attenuating. We can turn a marker on, and we can turn. We have 2 markers here. Let's go marker 1. So here's marker 1. So let's place marker 1 at 7 megahertz. Okay, and there's 7 megahertz. And then we'll say marker 2, we'll say marker 2 is at 14 megahertz. Now, if there's a harmonic at 7 megahertz, it's going to be attenuated by 35 dB, right? And if we go one step further, let's say 21 megahertz, it'll be attenuated by 65 dB. And so these are the 3 markers, and you can see the filters working here. And so, did we really need to do much to get a picture? No, we just hooked it up. And we've made it so that it's very, very fast. All right. So one of the things you can do is you can see that it's very, very sensitive to what's going on. Now, I've just noticed I have averaging on. That's going to slow it down. So let's turn averaging off. Okay. And let's go to our sweep speed. Yeah, we can sweep very, very fast, but now we have averaging off. So so now it's much, much faster. You can see how quickly it updates. Now it's doing its 31 milliseconds. Before I had it averaging a 4 on, so I needed to take 4 measurements. So you can see how quick this is. So if you're like winding a toroid, or trying to figure out something, or adjusting potentiometer and stuff, this is what you want. You want a very, very, very fast instrument. And so this allows you to tweak things in, and you don't really care about the bottom end. You really kind of care about the shape. You care about these markers, and yeah, that's all you really need to do. So you can turn this thing into extremely, extremely fast. Okay. So let's add some more data points. Let's go into the menu, and we'll set number of points. Here's 100 points. Okay. And you can see it's still very, very fast. Now we're sweeping 62 milliseconds, so it's a little bit slower, but gee, that's still pretty fast, right? All right. Let's see if we can't, well, one of the things we're going to take a look at here is the dynamic range of this filter. And right now we're measuring 85 dB of a dynamic range on this instrument, which is just totally incredible. Let's see how good we can make it, though. Let's see if we can set it up to make the very, very best measurement we can. We're going to do menu. We're going to set the number of points to, let's see, we're going from 1 to 40. We don't need 800 points. 400 points is plenty fine. So we'll do 400 points. And we can eventually turn averaging on, but we're not going to do that quite yet. We are going to set the system bandwidth. We can lower the bandwidth to 250 hertz, and you can see that our noise went way, way down. And we're already measuring great here, okay? So this is really, really nice. So let's go ahead and calibrate. Calibration will lower our noise as well, all right? So let's disconnect these. Let's disconnect these connectors, and we will do a calibration. Make sure that we're on the N-type calibration, not the default. Don't use the default. All right, so in order to make the very lowest noise measurement, we're going to do response plus isolation, okay? And so it's going to measure any crosstalk between these two channels and cancel that out. So it says connect loads to both cables. I'm going to calibrate at the end of the cables because that's where I'm going to insert the device under test. And so I'm going to put a load on each of these connectors. So we'll have 50 ohms on both sides. Everything will be very, very quiet. All right. And then we will say measure. All right. Then it says connect the through. And when we do a through measurement, what we're going to do is use a tiny little through here. This is similar to the one that would come in your cal kit if you have like a nano VNA or something. This one's a little nicer, stainless steel. All right, measure the standard. And there we go. It says calibration complete. We're getting a line exactly at 0 dBm, or 0 dB. And as we disconnect these two, our noise floor is now at -100. So that's very, very quiet. We have at least 100 dB of dynamic range. All right. Let's go ahead and do scale. I'm going to set the reference level to -40, just to see the very, very bottom of our calibration. All right, sweeping a little bit slow, but let's turn averaging on and see how low of a noise floor we can get on this thing. There's averaging 3 and now averaging 4. So we're getting a little below, the center line of that is probably about 105 dB. Looking at about 105 dB of dynamic range, all right? So let's put in our filter. Let's go back to scale. Let's go back to reference level of 0. We will input on the left and output on the right. hopefully this is in camera. And we will put this one in. And there we go. We are looking at our filter. And we need to reset our averaging, restart the averaging. There we go. So we're getting a pretty clean measurement now. It's coming down here to minus 85 dBm. Now, I did this measurement before doing the video, and I discovered something that just completely shocked me. Let's turn off averaging so we can see this real time. And let's see if we can speed our sweep up. Our sweep is pretty slow. It's 2.9 seconds. But what I did was I looked at this and I said, oh, okay, I'm gonna bend this little capacitor that way and that one that way, just so they're not close to one another. Okay, I moved them maybe 5 millimeters. And then let's see, we have no averaging on. You can see that our noise floor went down 5 dB just by getting those two capacitors out of the way. Let me bend them a little bit farther. And look at that. So this just shows you, so it's down at minus 100 dB now. Okay, all I did was move those capacitors maybe a centimeter apart, maybe 8 millimeters. This one was like bent like that because it was in a box, and you can see that already it's come up about 10 dB. And if we just separate the two, so these two capacitors are just talking to one another just through the air, okay? And if I separate the two, we're getting down here to the noise floor of the instrument, which is at minus 100. Let's go ahead and bump it up just a little bit so we can see a little bit better. Scale reference level minus 40. And then we'll turn averaging back on. And let's see how low we can get this measurement to maybe made. So we're down at the noise floor of the instrument. We're down to minus 105 again. So there you go. Just a demonstration of two things. One is you can go super fast if you're just doing experimentation. And then if you want to make super precise measurements, then you take care of cowling it the right way, making sure everything's okay. And then once you get a filter made and it looks good on paper and you've built one, then it comes to the point where there is a lot of mechanical considerations on filters. If you see some filters, each section is separated, and there might be a feed-through capacitor, and there might be actual Faraday cages around each section of the filter so that there is no crosstalk. If I, let's see here, let's go back to system bandwidth. Let's increase that so we speed up a bit. And let's go to the menu, number of points. Let's go back to 200. And let's turn our sweep speed very fast. So there we are, very fast. Let's put our scale at 0 again, 0. Oh, wait a minute. 10 and reference level at 0. There we go. And so this idea of having capacitors closer together, you see there it's going up when I have these capacitors close together, right? If I put my fingers on it, they come up. If I put my hand around it and then couple the signal across from one section to the other, you see that the rejection, now there's a path around the filter, right? There's a way for the electrons to get around. They're going through my hand, right? Instead of going through the filter, they're going through my hand. So there's a lot of mechanical things that you can do in order to make filters better. You can look at that online. There's tons of filters you can see, and a lot of times they're made with PC board dividers between the different sections and stuff. And that is to get rid of this crosstalk. And you can see that we increased this filter by 10 dB just by making sure that the capacitors weren't right next to each other. So there you go.